Hey folks, Robert Quinn here, your LinkedIn semiconductor industry content provider. I have Dr. Avi Messica here with me. I am so honored to have you on the show today. Thank you so much for joining us today. A little bit about Dr. Avi. He is an experienced serial entrepreneur in semiconductor optics and telecommunications and served in the senior management positions in companies like Tower Semiconductor. Avi co-founded and served as the CEO of Memlink. Avi also acted as the CEO of Doku Technologies. Dr. Avi Messica also served as the chairman of the public management of the startup branch at the Israeli Export Institute and as the council facility member at the Coleman College Management, as well as the advisory board on a few startup companies. Currently, Avi is the co-founder and CEO of NeoLogic. Avi holds a PhD in solid state physics from Weizmann Institute of Science. Avi, what an honor to have you on the show today, and thank you so much for joining us.
Thank you, Robert. It's nice to be here with you, and it will be certainly a pleasure to talk about all kinds of aspects of the semiconductors industry.
Definitely. I'm so glad you could join us today. And I know that we went through so much to try to get here between travel with travel and everything. It's so difficult for us to meet up, but I'm so glad we were able to do this today. Avi, as the co-founder and CEO of NeoLogic, can you tell us a little more about your organization and explain why power production reduction is important and how your company patents affect the market?
Yes, I think the answer can be divided into two parts. One is, the cloud. We are experiencing an increased overload of artificial intelligence, machine learning, data analytics, video tasks in the cloud, and all these apps or tasks require more and more computation power, which consumes, of course, electricity. And one of the aspects about it is that the data centers and cloud providers don't want to expand them because expansion costs money, and adding additional infrastructure costs, the utilities. And what people want to do is basically to take out a rack and put another one and have the same power consumption, but with more power computation. If you look at the edge, mostly mobile devices are battery operated, so obviously you'd like them to last longer. So in both, I think I would say verticals or dimensions, either the cloud or the edge, you want to save power. What we do in NeoLogic is since 2014, we don't scale transistors anymore, so we don't increase the packet density, and we don't have the historical Moore's law price performance improvement per generation. So what we do is we tackle the I would say VLSI design not via the physical dimension of transistor scaling down, but via circuits scaling down. And to put it plainly, what we do is we reduce the number, or if you'd like, the transistor count of circuits that are required to deliver any specific logic function. So if you reduce the transistor count of, say, a processor by a factor of 2 or 3, power consumption is directly related to the number of transistors, then you save power. And as you know, people say that, or the estimate is that data center consume roughly 3% of the total electricity bill of the world, and it relates also to the carbon footprint. So if you reduce the power consumption of these data centers, you also affect, the climate control in a sense. So we do that simply by reducing the transistor count of processors. Thereby, we reduce power consumption.
Wow, interesting. Interesting. And all through architecture.
Yes, we don't change the fabrication, we don't change the tools. This is merely a topology change. The way you place, if you'd like, the transistors in circuits. We do that at the standards level and also at the cells and blocks level. And the more complex the circuits are, the more we have, if you'd like to say, the more we have meat or transistors to shave off. And that's how we achieve it.
A chip called there's a chip called the Cerebus chip. Did you see that? It was
yes.
2.2 trillion transistors.
Well, it's an amazing, I think, technology demonstration of what you can do. Basically, it's an entire wafer is a chip, is a processor. And it has a huge, I think, computation power, but I think it also consumes a lot of power.
Mm-hmm.
And that's an issue.
Very interesting.
Yes.
Yeah. So you and I have both been in the industry for a very long time, and we've both lived the 200 millimeter world. We've lived the 300 millimeter world. What's driving the demand in semiconductor industry for both 200 and 300 millimeter? Can you talk about, can you tell me why the old 200 millimeter 164 nanometer technology is such in high demand, and what's really driving this sector?
Yeah, okay. This is my interpretation of what's going on or the trends in the industry. We should bear in mind that the chip shortage was not in the advanced technology nodes. The 10 nanometer or 7.5 there was no shortage or capacity in terms of production capacity in these nodes. The shortage was in 16 to 40 nanometers. These are where the automotive chips and all the I would say the mid price to low price processors are at, and these are manufactured in all technology nodes, even in planar CMOS, not necessarily FinFETs. And in those technologies, the wafer size is 200 millimeters. You have the 300 millimeters at the, I would say, at the high-end processors and the more advanced technology nodes. So, and since we have experienced this shortage, and there was a rush to increase the capacity of these technology nodes, then obviously what the equipment that is available is a 200 millimeter equipment. And bear in mind that these mid-priced or low-end processors are very cost sensitive. So the equipment cost and the wafer cost, and to my mind, even yield, the yield is a factor. The old technology, relatively speaking, I'm talking about, say, 16 and down, are relatively very cost effective. And in view of the chip shortage, this generated demand for via this mechanism for the 200 millimeter. We still see fabs that that will run on 300 millimeter wafers, but these are very expensive fabs. That's 10, 7, 5. This is a big players game. Apple, Intel, and all these guys. A small company, we meet a lot of meet to small companies. They can't afford these prices. And by the way, 16 is kind of the sweet spot. If you look at the foundry, say at the foundry profit margins, they are the biggest at the higher at the 300 millimeter wafers. But the volume there is not the profit per or the gain per wafer is higher at 300 millimeters. But most of the volume is 16 and 40. If you look at wafer count, 16 and 40, and 16 is the sweet spot. So no wonder why this is happening, I think, in the past 2 years or so. That's about it. I think also, if you look at maybe at the more historical trends in the past, we wanted to have bigger dies. And therefore we moved into, say, from even 2-inch wafers in the 60s up to the 200 millimeters today. But today we are not after big dies. Power, because the node scaling has broke down, so power limits us. So there's no point in kind of chasing for big dies. And you mentioned Cerebras, by the way, so there is a connection.
Yes. Yeah, I definitely see a and then we're going into the power semiconductors with gallium nitride, silicon carbide, and all this. I see a big demand for 200 millimeters sticking around, and it seems to be a big driver for the industry, and it's going to continue to be a big part of our industry globally. But I don't know if you remember, like when we were working on, in what was it, 1999 or so, we were working on 200 millimeter equipment, and we're like, oh, the 200 millimeter equipment's just going to go away. The 300 millimeter equipment is going to come in. They'll just get rid of that whole 200 millimeter thing, and it didn't happen. Right? It was kind of funny how that conundrum took place. But
yeah, I don't catch me with my being accurate, but I think that even today there are more 200 millimeter fabs than 300. It should be checked, but I think it still is the case.
I think you're right. Yeah. But there was a time we thought the 200 was just going to go away.
We did.
It didn't. Yeah, definitely. Well, Avi, where do you see the semiconductor industry growing geographically? There's a lot of regions such as India, and there's regions such as, I was just in Oman that's trying to get into the semiconductor industry. It seems like the whole world right now is trying to get into the semiconductor industry. Obviously Israel has been a big player in the semiconductor industry for a very long time. Do you foresee them growing? Like, what regions do you foresee growing around the world for semiconductor?
First of all, this is a dangerous question in a sense, and you should take whatever I say with a grain of salt. I think we are living in a polarized semiconductor world. We have two it's China with manufacturing capacity and the US with the design capability. I don't think geographically things will change significantly in the next decade or so. In fact, what I see is, advanced manufacturing capacity via TSMC, setting up facilities in the US on US soil. Mm-hmm. It doesn't mean closing the gap. On the other end, unfortunately, I do see China keeping its superiority in the manufacturing, and I do see them closing the gap. May I remind you that we in the West thought that SMIC will have 7 nanometer, I would say 2 or maybe 4 years from now. They have it now in pilot production. It took them 2 years to move from 12 nanometers and 7 nanometers, which raises some eyebrows. So I think the cards are favoring China. They will close the gap design-wise, VLSI design, within the next decade. Now, as for other regions, Israel has kind of lost some steam. Our semiconductor industry is not as it used to be. So we are even Israel is losing some ground. I don't see, India and some other efforts. Europe has its own CHIPS Act. You will see some, margin improvement, but I don't think globally things will change in the next decade. Apart from what I said in favor of China, they will close the gap in VLSI design. But again, I started with take it with a grain of salt, and I ended take it It's my view. I hope I will be proven wrong, but that's the way I see it. This, at least based on what we see today.
Yeah, definitely. There's going to be interesting geographical growth around the world, and we'll see how this race pans out. And it's definitely a race to the top. But Avi, I saw that you have a past life working in optics. I'm so interested about this because the optics are such an interesting growing area. Can you speak about optics and the growth of the industry? Where do you see this growth going? What equipment is used in the industry, and what are the processes used in this industry for doing optics? It seems to be a very growing industry with so many different sensors that we're doing today. All the new vehicles have sensors on them. All these are optics. And where do you see this industry going?
Yeah. Okay. Optics is one of my favorites. I will make some sort of a difference between what is going on in computer vision, which we had significant advancement via convolutional neural networks and all this stuff. I'll take that aside, and I'll discuss only the, I would say, physical optics. Okay, as you mentioned, some sort of sensors, maybe smart image sensors. I think, and again, this is my view. I don't think that. Let me kind of balance it. If you recall, 1995, we had Siena putting several, doing wavelength division multiplexing, and putting several wavelengths in a single fiber optics. Everyone knew at that time it's a revolution. Basically, we are now using it, and it really revolutionized the entire, I would say, optical communication. That was a revolution, and you felt the excitement in the air. So although some very interesting things are happening in optics, I don't see the same, I would say, impact, if you'd like. If you look at LiDAR, I'm not bullish on LiDAR, and I've never been. I think it's kind of a feature in a sense. It's not a revolution. And if you talk about, maybe some people talk about photonic computation, maybe, but not tomorrow. It's still in its infancy, I would say. You lack the scalability and integration. I've been there, I think, say 15 years ago, did integrated photonics for OEDMs in telecom on a gallium arsenide platform. We are not there yet. By the way, in optical communication, you do have some development that you could do that in integrated photonics. But I think what people are doing with photonics is that they are trying to compete with electronics, which might not, you want, this is what NeoLogic does. We don't compete with the existing paradigm where its strengths are. We look for weaknesses, and we kind of try to augment it and compete with the existing VLSI design paradigm in those dimensions that you have weaknesses. So photonics is in some sense trying to compete with electronics, and this is not where it's forte. For example, the wavelength division multiplexing is a huge, I would say, a classic example, because you can have several wavelengths, light wavelengths, carried by the same fiber. In electronics, you cannot, launch several, streams of electrons on the same copper wire. You can, or metal wire. You can't do that. So there you had a leverage. So unfortunately, I do not see, major advancement in optics. I mean, physical optics. We talked computer vision. We had really a jump in the way we can interpret the world. But even then, even there, if you look at all kinds of deep learning based computer vision, we got stuck now. So we had a jump, a significant one, and now we are at a plateau. So my view is that optics, you see some sort of, kind of small advancement, but not something that you might think of as making a revolution. That says, we see a lot of interesting things in optics. If for example, Apple will be able to put the non-invasive blood glucose measurement via their Apple Watch, that would be something, because this is the holy grail of blood glucose measurement, and it will affect people lives. So that might be really a breakthrough. But apart from that, I don't think that I see some sort of major breakthroughs or revolutions in the optics space. But the potential is there. It's merely people are trying to do also quantum computing via photonics, and there you do have some potential that you don't have in electronics. But you need to have lots of qubits. So there are some avenues where optics can pave the way to new advancements. But these are, at least at this stage, at the level of a potential rather than something that's happening.
Interesting. Yeah, I've always said that it seems like Europe has a great foundation for growing in the optics industry, because they just have so much potential for that there. But I've just always been curious about the potential growth of the industry, and will we see continue to see growth in it? But that's great. And the optics is basically CVD. Is that correct? Is a chemical vapor deposition process that's done.
Okay. Since you said, there is one major, I would say, contribution of optics, and of course, it's the the EUV lithography. Basically, it enabled us to do atom-sized transistors. But this has been accomplished, so I can't consider it as a kind of this revolution has taken place, say maybe 8 years ago.
Thanks so much, Avi. I saw that you had written in one of your papers. You have written so much, and I've looked at one of your papers about power semiconductor industry. What do you think about this sector, and will we continue to see growth in this industry, and will it scale to 300 millimeter, you think? I see a lot of growth in power semiconductor. We see Wolfspeed growing. We see a lot of it's obviously a big part of the industry, this wide band gapped industry. Where do you see this going?
Yes, I think wide bandgap semiconductors do see some renaissance in a sense, and this is one of probably the CAGR wise are the fastest growing in the semiconductor industry. I think driven. I phased out of this field, but but I do think that you have the mobiles, you have the solar powers, and you have the EVs, and all these verticals basically are driving these wide bandgap semiconductors. So there is a growth. I think this is the fastest growing segment in semiconductors. I haven't checked it, but I think the CAGR is on the scales of few tens % or so. But again, I'm not looking. You shouldn't go and check and say that it. I don't know. I think it's few tenths of %. And it will still grow because we are, although I'm not, kind of an advocate for, I don't think EVs are the way to go, but it will drive them. Base stations, RF amplifiers, it will drive them, and solar panels will drive them. So this is, I think, sector that will grow in the next, probably decade or so. That said, it's still a niche market if you consider the entire semiconductors market. But yes, it is a growing market and one to be, I would say, in some sense, envy of. If you look at other verticals of, my position is either from silicon and occasionally from gallium arsenide, whatever. So, silicon carbide, gallium nitride, I think these type of material-based devices are doing very nice these days, and it will continue to do so. That's about it,
I see so much potential. I see so much potential in power semiconductors, and I think it's going to be a great. I mean, of course, we're seeing a kind of like a downturn in the industry right now. Of course, memory is seeing a downturn. A lot of other sectors are seeing downturns, but the unlimited growth of power semiconductors is just vertical for throughout the next year. It's the growth. I
agree. But I think even more.
I'm curious if we'll ever see the growth see that move into a 300 millimeter sector.
Yes, I do think so.
Technology changes over time, possibly, right?
But not in the short term. It will go there eventually, but not in the short term. And also, I think the mix will be that only few fabs will run on 300 millimeters. Most of them, basically, it's like CMOS. Most of them will be 200. There is I would say, you should wonder why the industry, because at my time, even people talked about 450 millimeters. Why didn't we go there? Because at that point, at that size of a wafer, you have prohibitive costs in the wafer production. The ingot becomes too heavy. So probably the largest wafer we'll ever use, unless somebody comes, from the ingot size and this growth, crystal growth, and find some, breakthrough, we are currently probably cost-wise limited to the 300. And again, the same economics will apply to the WBG, because 200 is very cost effective. Equipment, wafers, whatever. So it will go to the 200. I think it will kind of plateau there, and you will have maybe 10 years from now, you might be mega foundries or fabs that will do the 300, but not too many.
Yeah, totally.
I think
so too. That's what I think is just as well. Shifting gears a little bit here. What are your thoughts? I wanted to ask you, where does Moore's law come to an end? Like, I mean, we're obviously seeing, we're hearing people talk about 3 nanometers, 1 nanometer. Like, I love teaching. Whenever I talk to people about semiconductor, I try to put these things into perspective, right? Like, and depending on what type of material it is, but 3 nanometers is roughly 21 atoms wide. We're stacking atoms. This is incredible, right? The technology that we're getting down to.
I don't think there is 3 nanometer. Well, based on the facts that I get, or from I think that we have got that humanity has got stuck in 10 nanometers. This is the best that we can do. And as you said, look, it's amazing. It's few tens of atoms. Okay, so and by the way, this is one of my favorite topics, and you give me an opportunity to debunk some myths and interpretation of people about Moore's law. First and foremost, Moore's law, Gordon Moore. People say that it's not the transistor size, but the economics of Gordon Moore never discussed the economics. In fact, there is one economic prediction that he made in his original paper, and time has proven it to be completely incorrect. What has been proven to kind of become kind of a self, fulfilling prophecy is the log-based 2 advancement. But mind you that in Moore's original paper, I think it was 65. Gordon Moore published his paper in 65. He was working with Fairchild. Technology started in 1959. He had something like 5 data points, and based on that, he plotted a graph that simply putting the maximum number of transistors per chip. That is the graph. It doesn't relate to transistor size. By the way, if you delve into the paper, you'll see that Gordon even relates or attributed some of these advanced of log-based or exponential, basically, advancement to the metals width and pitch. Okay? But later on, it was translated, of course, to the transistor scale down. So the real fact is that Gordon Moore never talked about scaling the way transistor, the way we kind of interpret it. He discussed the maximum number of transistor per die. And by the way, at that time, wafers, we talked wafers, 2-inch wafers. And he projected it 3-inch wafers. How many dies and what is the maximum number of transistors that we'll be able to pack into dies on a 3-inch wafer? That was his prediction, and it turned true, all the way up to say 2004. So why 2004? Because 2004 the Nard law has been broken down. The Nard law is basically saying that the on the same token that you scale down transistor, you scale down power. In 2004, it broke down. You shrink the transistors, but you didn't shrink the power consumption. And this is why this is why they went into cores. You have 50 billion transistors, but most of them don't operate. They don't work. You have multiple cores, but only few of them work. So I think Moore's law has been dead and gone probably when we switched from planar CMOS to FinFETs. We pushed it a little bit, 10 nanometer. This is the end. And if you look at SEM images, for example, of TSMC 7 nanometer, you'll see that physically it's equivalent to Intel's 10 nanometer. And the 7, 5, 3, 2, 1 are not shrinking our marketing terms. You don't shrink the transistors anymore, but you do shrink, as by the way, it goes back to 65, to Gordon Moore. You do shrink the cell height, you do shrink the width of the metals, and the pitch between them. This is how it's been, how we've been succeeded to get additional, say, improvement since we introduced FinFET. And by the way, since we introduced FinFET, the price per 1 million transistors has gone up, where it was going down up to that point. So Moore's law physically probably has been dead and gone in 2004. We succeeded to shrink them up to the FinFET 16 nanometer, say 2015 or so. No wonder it took Intel something like 6 years to switch from 14 to 10. It's difficult. And since then, what we've been doing is basically reducing the cell height and reducing the metals width and pitch. That's the way. And this way, you don't get, say, 100% improvement per generation. In advanced technology nodes, you get something like 5%. And you get terrible yields. And I will not go further into that because I don't want to get into trouble with all kinds of organizations and foundries. So that's my view, and in this case, I think it's a sound view of what we've been experiencing when we switched to FinFETs and when we switched to multi-cores in 2004. And that's where we come in. Basically, we come in this most of our unique value proposition is in the advanced node, because in the advanced node we can give you, basically we can get you as our customer, you can stay on your 16 nanometer, use our technology, and you'll get the benefits of 10 nanometer and maybe 7. We can kind of leapfrog you one or few generation ahead, because we deliver more than 5 to 6% per generation.
Yeah, definitely. And we'll continue to also see like 2D packaging and the way that we're packaging the chips, and will we continue to see growth in that area as well?
Yes, I've been working for Shellcase, which was wafer level chip scale packaging. And I do think if you look at packaging and you see, by the way, what is called chiplets at my time was called multi-chip module, and they changed the terminology, but it's the same. And I think that we will get, I would say, we will be able to push the envelope of the performance. It's everything is in cycles. We are now getting back into what was called in the 70s or 80s ASICs. We are now calling them accelerators. So we will have a special purpose processors put on it as a chiplets, and you will get the extra, or we will push the envelope, say, for the next decade or so. Packaging will definitely go 3D. I think also in terms of processors, via the chiplet approach, memories we already have huge 3D. So and by the way, even in VLSI itself, we are now shifting into the gate-all-around, which is a sort of a 3D concept, because we will have multiple whatever you name it, conductors or whatever, or transistors at the nanosheet or whatever as they call it. So we will also go there, but we won't have the same, I would say, scalability and packing density as we have in packaging and chiplets, because we will affect because gate-all-around is not you have transistors in stores as you do have in memories. Basically, the gate-all-around, you will have several transistors, but they will several polys, but they will be controlled by a single gate. What does it mean? It means that you have a packet density in terms of the driving strength. You will not need need to put 4 transistors in the plane in order to get a 4x driving current. You'll put them in 4 stories high. So it will improve density. Yeah. So 3D is going also to the plain vanilla CMOS FinFETs, and we will see also improvement this way.
So interesting. Well, Avi, thank you so much for joining me. I would like to thank Move Technologies for sponsoring this Movers and Shakers show. As we deep dive into the semiconductor industry with some of the top industry leaders like Avi. If you have any used or refurbished semiconductor equipment, or you would like to buy and sell, or please feel free to reach out to me, or check us out on LinkedIn, or you can check out our website at www.moov.co. Again, Avi, thank you so much for joining me today. This has been so informative. It's been amazing talking to you, and just one of the greatest minds to be able to hear your thoughts on this. This is great, and thank you for joining us.
Thank you for having me in your show, Robert.
Thank you so much. Have a good one, Avi.
Thank you. Have a nice